All right, so the boiling points of alkanes increases as the number of carbons increase because of the increasing amount of surface area and the increased amount of van der Waal attractions. We've kind of talked about this on last chapter. But you can see here, these are straight chains. The blue line is based on straight chains. If you have straight chain alkanes, all right, so starting with 1 carbon, 2 carbons, 3, 4, 5, you can see it drastically, exponentially increases. Then once you have more branch chains, which is the green line, they're a little bit lower because you have less van der Waal attractions. So when you get more branching groups, you're it's the same situation. You're increasing, but it's not as much as if you were straight chain. All right. Also, melting point, same exact thing. The melting point increases as your carbon increases. Alkanes with an even number of carbons have higher melting points than those of odd number of carbons. Okay, which is a very interesting criteria, or I'm sorry, a very interesting phenomenon. But it's almost like the same type of thing based on the interactions. All right, alkanes. These are kind of sources of alkanes. Well, where do we get alkanes? Alkanes is a huge industry. They are obtained by petroleum and petroleum byproducts. So when we extract out natural gas and oils and fossil fuels out of our planet, we actually isolate a lot of these alkane sources. Fractional distillation is kind of the way that you do to separate it, which means you distill hydrocarbons and you can distill out different weight alkanes or size alkanes, and then you can take those and further distill them as well. Other ways of getting smaller alkanes is called catalytic cracking or hydrocracking, which is basically a hydrogenation process. You can see by adding hydrogen and heat and a catalyst of some sort, you can actually break these in half. It takes a tremendous amount of energy in order to do this. But you can break these to half into smaller alkanes. You can even take them and get different type of shorter chains with a double bond, some with triple bonds, and things like that. All right, this is kind of how we represent methane. All right, we're going to start talking about the conformation of these molecules in the second half of this chapter. All right, and we've talked about this. Methane is tetrahedral in shape, 109.5 degrees. They even gave you a bond length. All right, this is the way to write them. This is kind of a ball and stick figure. This is called space filling model. This is actually what we think molecules look like. They actually aren't little sticks and balls hooked together. All right, it's these blobs of electron clouds where you got this big carbon one, and then you have hydrogen that in its s orbital kind of sharing the electron in them. So this is kind of more what we think molecules look like. All right. So again, it's tetrahedral, sp3 hybridized. A representation of ethane. Again, you can see the carbon-hydrogen model. All right, again, 109.5. They give you bond lengths. The carbon-carbon bond length is bigger than a hydrogen bond length. Here's kind of a stick and model model of it, and then here's kind of more the space filling model. All right. We're going to kind of talk about the shape of ethane and how it's the conformation of it. So ethane has 2 sp3 hydrocarbons. There is rotation around the sigma bond. All right, so this bond right here, you've got rotation around that, which would be this bond right here. All right, you also have rotation around the carbon-hydrogen bonds, obviously, but you can't tell because you just have a hydrogen spinning. But this, this whole thing can actually spin around, kind of like a fan in a way. All right, the conformations are different arrangements of atoms caused by the rotation about a single bond. So we're going to look at different conformations of ethane and larger alkanes. Okay. So again, here they talk about the rotation. You have an overlapping sigma bond here. All right, so you can rotate around this bond. So they're kind of trying to show you this. You notice how these two hydrogens right here, or actually all the hydrogens, are in the same plane or are parallel to each other. So this hydrogen right here, all right, let me get my pen here. This hydrogen right here, notice, is parallel with this hydrogen. And this hydrogen right here is parallel with this one, meaning it's in the same plane. And this one in the back is with this one in the back. Okay, so they're kind of parallel. All right, now if we rotate around this bond, here they're kind of showing you, imagine I'm looking at this molecule this way. I'm looking at, so this carbon right here is this carbon right here. And this carbon in the back, I'll put a square around it, is this carbon in the back right there. And you're just kind of rotating this around. You can see that instead of having this hydrogen and this hydrogen, these hydrogens parallel to each other, see it's kind of turning away, you can actually have them alternating each other. It's called staggered from each other. So now you have a hydrogen in the plane here, but notice you don't have it in the plane here. It's in the plane at the bottom. Okay, so let's see what this says down here. Pure conformers cannot be isolated in most cases because the molecules are constantly rotating. Okay, so it's basically saying I can't isolate one of these molecules because this is constantly rotating. However, we're going to find out that one of these conformations is what this molecule prefers to be in most of the time. So it's kind of rotating, so it'll kind of go and then it will go back into the more stable conformation. So we're going to talk about what's called a Newman projection and how we can look at these molecules and see how they rotate. Okay, so here we go, Newman projection. Here's your eyeball. Okay, we're looking down at this carbon-carbon bond right here. We're looking down this carbon-carbon bond. You're always, when you look at a Newman projection, you're looking down some sort of carbon-carbon bond. That's your perspective. Okay? And what you're doing is you're looking at the three things each of these carbons are attached to. Let's call this carbon 1 and call this carbon 2. This carbon 1 is attached to these three hydrogens. 1, 2, 3. This carbon is attached to three hydrogens. 1, 2, 3. Okay, so what you do is you look at the relationship of these three carbons with respect to the back three carbons. All right, so notice they have this in black, and then they have the back ones in pink. So this is kind of what it looks like if your eyeball is looking at it this direction. So this right here is the black carbon, is this carbon right here. It's carbon 1. Okay, and these are the three hydrogens attached to it. And then in the back are the three pink hydrogens. Okay, and the way this conformation has, notice here you have a hydrogen, you know, straight in the plane, but you have the other two hydrogens kind of flanking on either side of this hydrogen, which is what you have here. Here's the hydrogens going straight up and down. This hydrogen is that hydrogen, and then you have the two here in the back, which are these two. Okay, so notice it's alternating. It's hydrogen, and then but you have nothing in the back near it. It's to the side. It's in between. It's flanking in between these two hydrogens. Okay, this is what we're going to find out is called a staggered conformation. All right, and this is the more stable conformation because if this hydrogen, if you rotated this hydrogen so that it's parallel with this, the two hydrogens kind of hit each other. All right, and we will see it on the next page right here. Okay, you see these two hydrogens? This is called the eclipsed conformation. They're eclipsing. Everything is parallel. This molecule is very similar to this molecule up here. Okay, this molecule up here is eclipsing, where the hydrogens are parallel to each other. Okay, so this is eclipsing. You have a zero angle here. It's called a dihedral angle. Okay, you have a zero angle. These are parallel. These are hitting each other. It's called steric interactions. You kind of have these steric interactions with each other. Okay, but when you rotate it and you put them like this, you now have them staggered, you alleviate some of that interactions. This up here is kind of showing you the energy. So the y-axis is energy. Here's your highest crest of energy, and here's the low point of energy. Okay, so this eclipsing interaction, you have all these interactions here. Okay, and that interaction is causing the molecule to be more higher in energy. As it rotates, so as it's rotating, as this hydrogen starts moving to this area right here, you alleviate a lot of the energy. So this molecule represents this energy now. And then if this just keeps rotating, you're now back up to a higher energy. and then if it rotates out, it goes back down. Don't worry about the numbers. I'm not going to worry about any of the numbers. But basically, I want you to understand that if it's in eclipsed, higher energy, staggered, lower energy, low energy. Okay, so they talk about that the torsional energy of ethane is lowest in the staggered. Okay, the eclipse in conformation is higher in energy. Again, don't worry about a number. At room temperature, this barrier is easily overcome and the molecules rotate constantly. Okay, now let's look at the same thing but at propane. Okay, again, we're looking down the C1, C2 bond. This is C1, this is C2. This right here is C1, and in the back, behind it, you can't see it, is C2. Okay, and again, what we're looking at is we're looking at these two carbons and the three things those carbons are attached to. In this case, it's a hydrogen, and a hydrogen. In this case, this carbon is attached to a hydrogen, and a CH3 group. So you don't look at the Newman projection of these hydrogens with respect to this carbon, because we're just looking down these two carbons. So you notice down here they have it as a CH3. They don't have all the hydrogens in 3 dimensions because we're looking at the relationship between these 3 hydrogens and these 3 groups behind it. Okay, so here's a Newman projection. This is the staggered conformation. This is the most energetically favorable conformation, because think about if we rotate this to the eclipsed and this methyl group is right near this hydrogen, you're going to have a lot of interactions there that's causing it to be high in energy. Okay, so let's see, propane is shown here as a perspective driving. Okay, we already talked about that. Okay, so here we go. Let's look at all the conformations. You have the eclipsed conformation. Okay, methyls and hydrogen. Okay, now again, I don't care about the numbers, but notice in the last one when we talked about ethane, it was 3.0 kilojoules. Now we're at 3.3 kilojoules, so we're increasing in the amount of energy. And 1 kilojoule per mole is a lot of energy. So 0.3 is quite a bit. It doesn't seem like a lot, but it is. Like I said, we're not going to worry about the numbers. Just notice that it is higher in energy. Okay, higher in energy. This molecule, oops, sorry about that. This molecule right here represents that energy. As soon as you start rotating this and you're now staggered, this represents that energy, so forth and so on. Okay, so the staggered conformation is lower in energy than the eclipsed. Okay, since the methyl group occupies more space than the hydrogen, the torsional strain. So it's called torsional strain. I also call it steric strain. All right, these are sterically hitting each other. Okay, the atoms are actually, are bumping into each other. It's not good. Now let's talk about butane. Butane is 4 carbons. Okay, here's butane. This time we're going to look down C2 and C3. We're looking down this bond and the 3 things that's attached to. 1, 2, 3. 1, 2, 3. So this carbon is attached to these 3 things, and this carbon's, notice it's 2 hydrogens in a methyl group. All right, now how much? So here we have an eclipse, and then you rotate. So let's just look at the Newman projection. These are eclipsing. Look at that. I mean, how much energy do you think? I have a huge methyl group here and another methyl group here interacting with each other. That is really bad. Now, this comes out to 60 degrees. It's not eclipsing each other or staggered, but they're still close to each other. Okay, you still have 2 large groups close to each other. That's called a gauche interaction. This word is gauche. It's French. I've heard 2 meanings for it in French. For those that speak French, maybe you can help me out. One of them, I've heard the word left. The other one, I've heard the meaning of off-center. Off-center would make more sense. However, gauche, I think, is also left in French, but that doesn't make sense. I guess one is left to the other. I don't know. But I've heard off-center. So this is a gauche. Gauche only happens when you have 2 large groups, non-hydrogen groups, okay, that are staggered to each other but are 60 degrees from each other. So you still have an interaction here, but it's not nearly as bad as this. This is really bad. This is better, but not great. Okay, if you keep rotating it, you're now going to come to an eclipsed again. Again, we have steric interactions or torsional strain, still bad things. And then when this rotates to here, you have what's called the anti-conformation, where your 2 largest groups are completely opposite each other. This is the most stable conformation. Right? This one is the least stable. And the ones in between are a little bit more stable. Okay, so butane has 2 different staggered conformations. The gauche, or gauche, 16 60 degrees and then the anti. The eclipse conformation, where dihedroyl methyl group is 0, is referred to as a total eclipsed and incredibly unstable.